This week I want to go over multiple regression. And multiple regression is simply adding additional independent variables into the model. Last week we focused in on simple linear, and simple linear, as the name implies, is that it's simple because we're only dealing with one independent variable. And the reason why we add additional independent variables is to help explain away the behavior of what is going on with our dependent variable. If you recall, the focus was on the r-square of the coefficient of determination. And that coefficient of determination, let's assume, say, 60%. And that simply means that 60% of the behavior of our dependent variable, that would be the reason why the values change from one to another, can be explained away when we have a specific independent variable. So if we're only explaining 60% of the behavior of the dependent variable, that must mean that 40% is not being explained away. So therefore, we should be thinking about adding additional independent variables to increase, say, from that 60%, say, hopefully to get it to 1. Because keep in mind, as we explained last week, as I explained last week, that r-squared, that coefficient of determination, can take on values from 0 to 1 inclusively, whereby, of course, 1 or 100% is perfect correlation. So that is the reason why we want to add additional independent variables to the model to explain away more of the behavior, what is going on with our dependent variable. So to do that, we've added additional independent variables. Here, the example I'm going to go through is I have my my dependent variable y, and I have 3 independent variables, x1, x2, x3. What we want to be careful is that when we add additional independent variables, we want those independent variables to be independent of each other. If they are dependent upon each other, we refer to this as collinearity. Collinearity is a measurement, you might say, of how dependent independent variables are to each other. So we don't want collinearity, and our, you might say, demarcation point is that, in other words, if correlation between two independent variables happens to be, say, 70% and above, we would say we could have a problem. Collinearity could exist, which would, of course, would have a negative impact on the results of our model. So as I said, the first thing that we want to do, we want to see if we have any collinearity. So what we will do, as we did last week, we will go to our data, get our data analysis pack going, and go to correlation. And what I'm going to do over here is we're going to input the range, and the range will be everything, as I've indicated here, from Y, from cell A1 down to D3, as I've indicated here. Make sure you have your labels, and then, of course, just go ahead and say OK. And then you can come up with this correlation matrix. And here you have your correlation matrix. First of all, focus in on the relationship between our independent variables. So, of course, if I look at x1 and x1, of course, the relationship is going to be 1. If I look at the relationship between x1 and x2, here we have a coefficient of correlation of almost 71%. So right off the bat, red flag, red flag. That could be a problem in the model. If we look at x1 and x3, 58%, that seems to be okay. And if we look at the relationship, the coefficient between x2 and x3, 64%, seems to be okay. So it looks like we got a problem, a potential problem, that we do have a relatively high degree of dependency between independent variable 1 and independent variable 2. The next phase, since I'm focusing here on stepwise regression or stepwise multiple regression, is that I want my model to be robust, because in regression analysis, I'm trying to forecast something. I'm trying to forecast the value of my dependent variable using independent variables. So therefore, in the stepwise approach, I'm going to add one independent variable at a time, test it to see if the results are significant. So what we do from that standpoint is that, in other words, we want to enter, as indicated, one independent variable at a time. Well, here I have 3 independent variables. Which one will get into the model first to test? Well, in that case, in other words, I'm looking at column B, which is y, which is my dependent variable, and I'm going to do a correlation between y and x1. I get 58%. Y and x2, I get a coefficient correlation of 64%, and a coefficient correlation between y and x3 of 99% for x3. Very, very high. So the one that I'm going to test first in the stepwise approach, as indicated here, would be x3. I'm going to run that through the model first. Then, if that is significant, I'm going to run x2 through the model. And then, if x2 is significant, which I'll show here momentarily, and then I'll run x3. That's what we mean by stepwise multiple regression, is that I'm going to take one independent variable at a time into the model. Let's go back to our back over here to our data. And once again, I'm going to get into data analysis. I'm going down to regression. And it's going to ask me for my y range. And then it's going to ask me for my independent variable. And since x3 is going to get into the model first because it had the highest degree of correlation with my dependent variable. Always mark your labels, right? And then simply go over here and click OK. And we'll get x3. And these are the results. These are the results. We want to test it. As I indicated last week, right? In other words, we're looking for slope. If there is a slope, we will say that there is a relationship. And in this case, we can prove statistically that there's a relationship between my dependent variable and my dependent variable and my independent variable x3. That's good. That's good. And we did that by the p-value. If you recall, it would be something like this. The null hypothesis, there is no relationship between independent and dependent. The alternative hypothesis would be, yeah, there is a relationship between dependent and independent. And then, in other words, we assigned, a level of significance or an alpha level. And let's assume we're going to use 1%. So what we would say, reject the null hypothesis if the p-value for my slope is less than the alpha level of significance of 1%. Well, as you can see here, I highlighted in yellow, we're looking at, this is my intercept. In other words, this would be, if I was going to write out the equation, I would say y is equal to my y-intercept, negative 3.1, plus the beta, or the slope of 0.97, to my third x, we'll say x third independent variable. So this is our p-value, 5.616 to the estimate negative 0.9. That simply means, as indicated last week, I'm going to move that decimal point to the left 9 places. Well, definitely what? I have a p-value that is less than, less than my level of significance of 1%. So x3 is in the model. x3 is in the model. I'm going to save it. I'm going to keep it. It is significant. Okay, I go back to my data. x3 was first. Now I'm going to put x2 in with x3 to see what happens. And go back to my data analysis. Hit my regression. Put my y in. Put my x range in, which of course this time it's going to be x2 and x3. Putting that range in, as I've indicated here. I'm going to put my label. And then, of course, as we did previously, I'm going to come over here and hit OK to get it going. And then I'm going to come to my x2, x3 results, and I'm going to analyze it as such. Now, one thing that's very, very interesting, when we have more than one independent variable, go back over here. When we have more than one independent variable, we always will look at the adjusted R-square. And the adjusted R-square kind of takes into a margin of error. I just want to point that out. So, more than one independent variable always on in Excel. When you have your summary results, it's always the adjusted R-square. So when we come down here, once again, we want to analyze it, right? Is the additional independent variable x2 that I added to the model significant? Well, we can go back and we can analyze our slopes. If we analyze the slope for x3, right? We have 3.68 minus 0.7. Move that decimal point to the left 7 places, and definitely what? Yes, x3, when we added x2, is significant. Less than 1%. But look here what happens. Look here what happens when we look at x2, the slope for x2. Well, we have a p-value of almost 75%, which is definitely greater than our level of significance of 1%. So this is telling us what? It is not significant. P-value greater than 1%, or p-value greater than the level of significance, indicates there is no relationship. There's no correlation involved. So we don't want to include x2. We do want to include x3 into the model, because that, statistically speaking, is telling us there is a significant relationship between my dependent variable and my independent variable x3, not with x2. So therefore, since x2 doesn't get into the model, there is no need to go back and add x1, because if x2 doesn't get into the model, x1 does not get into the model. So if we kind of look at what's the best model then? What is the best regression equation to use? If I had x1, x2, and x3, well, the best model is x3. And that would be my regression equation, my intercept, and my slope. That's the model to use to forecast y. It is not including x2, it's not including x1. It is only x3. So when in this particular example we had x1, x2, x3, the best forecasting model, i.e. regression, would be to only use x3 as such. So that's multiple regression. More specifically, we refer to this multiple regression approach as stepwise.